Okay, I can see we've got quite a few people in the room, so I think we'll make a start on today's GPR-Slice session. Thank you very much for joining us. If there's anyone who's new to the webinar Jam platform that we're broadcasting through, there's a couple of things to point out. First is that somewhere above my head, just up here, there should be a reconnect button. And if the feed drops out for any reason, then the quickest thing to try first is press that button, and hopefully that will reconnect you. It's just a bit quicker than logging out and having to enter all your details again. Then down this side we have a chat function. You can use that for sending messages amongst yourselves, but you can also send us questions during the presentation and we'll do our best to answer them as we go along. There'll be time at the end as well to add extra questions, and I'll cover off anything that I missed during the demonstration. You'll see at the bottom, I think it is, that you should be able to choose whether it's a public or a private message. So if you have a question that is very project specific and you prefer the rest of the audience not to see it, then just mark it as private, and the only person who will read it will be me. Right, let's make a start. I'll get the presentation running. And I'll start just by giving a little bit of background about myself. My name's Jimmy Adcock. Confusingly, I'm the product manager for our ABEM range of systems, which are resistivity, seismic, and TEM. But before I joined Guideline Geo about 5 years ago, I actually worked for almost 13 years for a survey company in the UK. And for almost the entirety of those 13 years, we were using GPR-Slice. So that's how I've kind of ended up straddling the Marla and the ABEM sides of the company. And for those who aren't fully aware of how Guideline Geo, ABEM and Marla fit together, I've thrown in a couple of slides about the business itself. Effectively, Guideline Geo owns the ABEM and Marla brands. We have offices that are spread across the globe, as you can see from this little diagram. We cover most time zones pretty well, and these offices are a mixture of some sales, some technical, some mixed. The key ones are probably our head office, which is in Stockholm, then our research and development office, which is a bit further north in Umeå, and then further north again in the town of Malå. We have our factory where all of the ABEM and Marla systems are manufactured. In terms of the history, how we've got to where we are today, we can go back as far as 1923 when ABEM was formed to look into the possibilities of detecting minerals using electrical methods. Then Malå grew out of a Swedish geological survey office in the town of Malå. Since then, they've kind of grown and developed. But 2013 was kind of the key date when Guideline Geo brought together Marla and ABEM under the same roof. Today, we're going to talk about GPR-Slice. It's a third-party software package built over the years by Dean Goodman. It's a very versatile piece of software. It's also a very comprehensive piece of software, and trying to cover the whole thing in an hour is very difficult. So today's session really is just a brief introduction. Although not that brief, this will probably run to about an hour and 20 minutes, something like that. The plan would be that in coming months, we'll do some more focused sessions where we look at either a single processing technique or a single methodology or a single application. We've been a distributor since early 2019, and you can obtain subscriptions for the software from us, and if you do, then we'll be backing that up with both support and training. This presentation really is to try and make first steps with the software much easier for you, and also help you understand whether, if you're not using it already, whether it's something that would be suitable for your requirements. Now, GPR-Slice will accept data from pretty much every GPR on the market. So it doesn't matter what your existing equipment is and what your planned future purchases might be, GPR-Slice will be compatible with those. Now, in terms of Marla equipment, which obviously I'm going to be focusing on, it has some built-in import filters that allows us not only to just pull in the individual radar grams in the RD3, which is the 16-bit format, or the RD7 32-bit format, but it also allows us to directly open up 3D grid projects it allows us to automatically open up object mapper projects, and we can also import very simply the mirror data, and that's either from the existing regular mirror that's been around for many years, or our very new mirror HDR equipment, which we've just launched. In terms of what you can output from the software, the sky's the limit. From the very simplest would be radargrams, and they can be either flat radargrams or they can have topographic corrections to them. And the topographic corrections are very clever, because you can choose to either just offset the traces based on the elevations that you have recorded, or you can ask the software to calculate, based on those elevations, what angle the instrument would have been pointing as it went up and down the slopes, and will then adjust the geometry of the traces to reflect that. So radargrams, we can generate horizons, so we can go through and map surfaces, and then we can extract just the surface that we're interested in. We can do calculations based on volume between surfaces. We can take our radargrams and we can put them into a 3D volume, so that we've got a cube of reflectivity. We can then, once we've got that cube, do clever stuff like strip away all of the quiet areas where we don't have any reflections and just leave behind the strongest responses. We can do the traditional time slicing, where we basically have a map of reflection amplitude at different depths. And then we can get on to sort of the more complex stuff, such as vector processing. So in this instance, rather than just having an antenna that is positioned in X, Y, and Z, we're also defining the direction in which the radiation has been sent out and the reflections are coming back from, which allows us to do very complex shapes, and then that allows us to build the data set up with sort of transillumination, if you like. So having the antenna transmitting and receiving from all sides and generating a single data set from all sides of, for example, a column. And then another thing that we can do, take plots of the data, and rather than look at the reflection strength, we can look at the amplitude of different frequencies. And that can be very useful. Say, for example, where you have moisture, then the higher frequencies will be absorbed much quicker, attenuated much faster, and so they will have a much lower amplitude. So it's a very good way, for example, detecting moisture changes in the ground or within some kind of material. As well as different processing algorithms, the software allows us to actually automate some, and that's called blue box processing in GPR-Slice. And the reason it's called blue box processing is that the strict definition of a black box process is that you put something in one end and you get a result out of the other, and you don't know what happens in the middle. It just does it all for you. But in GPR-Slice, it's slightly different. We put all of the data in one end, we define some parameters in the middle, and then it will automatically process and give us the result. So it's not entirely automated. You need to make some decisions about certain processing setups, but it does allow you to throw data in at one end, and it will then work away doing all of the steps for you to give you your chosen end result, whether those might be a 3D volume or extracted time slices, whatever they may be. So let's have a look at the generalized workflow. It doesn't really matter what kind of data you're processing. The main steps tend to be the same. And so the first thing to do is to generate a working area. So this is just a set of folders in which our raw data and our processed data and our exports will all be kept. Then we import the data in its native format, whether that's our systems or some other companies. That gets dropped into the raw folders. And then we just need to tell the software where the profiles are. We have the option to do some editing on these as well, especially for the GPS data. We would then convert from the native format into GPR-Slice format. That kind of goes without saying. And then we can add positional stamps in it. So a lot of systems have a data file and then a position file, and they are somehow interrelated either by timestamping or trace numbers. And what GPR-Slice will do is take those two data sets and combine them into one by putting positional information into top couple of samples of the data. And that means that then from here onwards, we only have to worry about one file per traverse. We don't have to worry about any external positioning. After we've done that, we can start our processing and our filtering, the usual kind of processing that you'd expect to do for a GPR dataset. And at this stage, we've got two options. If it's regular kind of single channel data, we could look at the radargrams and process those, do our interpretations on them, export our interpretations. So if we've been, for example, picking utilities, we could export an XYZ of that. If we've drawn in some horizons, then we can export those either as XYZs or other formats. If we're using multi-channel data, so by this I mean like true 3D systems like our mirror, at this stage we've done all the processing we need to actually compile a 3D volume and to then do our visualization of that data. So it's pretty quick to get to that stage to have a usable data set. So this is kind of the first stop-off point on the processing workflow. If we've got our just single channel data where the line spacing is generally quite a bit bigger than the sample spacing along the line, then we would go through some extra steps to be able to generate our time slices, these amplitude maps from different depths. And this is where GPR-Slice differed massively from software that had gone before it. This was the genesis for the software, and it was the fact that almost all of the commercially available software that made slices didn't account for the fact that you have a much higher density of data along the line than you do between the lines or across line. And it gave you some really, in the worst cases, really horrible artifacts in the final slices. So GPR-Slice came along and said, well, here's my very high density of data inline. What I'm going to do is bin that into a much less dense data set along the line. And it sounds entirely counterintuitive. It sounds crazy to throw away that data. But actually, when you're generating the time slices, it gives you a cleaner slice and allows you to see more detail. Now, the raw radargrams aren't affected. The processed radargrams aren't. So whenever I plot a radargram, that is still at the original native resolution. But the data that we use to generate the time slices is desampled. From those desampled radargrams, we generate coarse slices at the different depths. And once we've generated those coarse radargrams, then we can interpolate to generate our nice final images. So at this stage, we can look at those 2D images, we can do interpretations on those, we can export them to a number of different formats, whether it's a geotiff, whether it's a surfer format, whether it's just a very simple XYZ. Well, we can actually then move on further and we can use those slices as the basis of forming our 3D volume. So steps 7, 8, 9 and 10 are the additional steps required to create a volume from single channel GPR data, and 1 to 6 is all you need to do to generate a volume from like a true 3D data set from a multi-channel system. So that allows us to do our full range of visualizations. So that's like volume plots, ISO surfaces, slicing, cutting it in any direction. And then we can do post-processing on the block itself. So we can actually take that volume and apply additional filters to it to try and further refine what we're looking at. And then again, export from there to different formats if we want to incorporate this data in other software. So let's have a look at how this generalized workflow then translates to the actual software itself. So here's the interface. This is what the kind of software loads into. And by and large, the processing, certainly for single channel data, you can go through the menus from left to right, working your way from top to bottom on each menu. However, there are a couple of quick buttons on here that give us extra options or shortcuts. So these N3 are for viewing time slices, viewing radargrams, and viewing 3D volumes. The first one, the project button, that allows us to jump back into any project that we've previously worked on to continue processing or do other visualization. Next is the folder button. Folder allows us to see all of the data files that are currently contained within the project area. So the project area is shown at the top, and these are the files within each of the subfolders. And this is very useful just to kind of show you what you've done in terms of processing, so you can see which of the filters you might have applied. And if we have any images, we can actually just click on them in here and it'll open up in a viewer, just a really quick way to see some of the exports. And then the final button is the options. This one is a frankly terrifying looking menu. There are so many options in here, but actually they're grouped into kind of like type settings. So we have like options for the color plots, the color scales. These are also accessible from any of the visualization menus. Then we have options for the plotting on the axes, various other options. But really the main reason for me coming into here is to talk about the multi-thread processing, which we can switch on or off. And this allows us to really speed up the processing that we're doing. It can use the individual cores on your processor to divide up the work of applying filters, for example. Now, the only caveat is that the way it does it is it sends off individual radargrams to the different cores, processes them, and then pulls them back. So that means that if your data set is just a single long profile, the multi-thread processing isn't going to speed anything up. However, if you've got a lot of radargrams, you will see a huge improvement in terms of the processing speed. Okay, so generic processing step number 1 was to create the project and set up the working folder. So that's in the file menu. And as I say, we're going to work top to bottom, create the new project. So in here, it tells us the kind of parent directory. Then you add in your survey name, and the survey name will be a subfolder underneath that parent directory. We choose the type of system we're using. That will automatically add in some settings, so kind of certain assumptions will be made based on what you've chosen here. Once we hit new survey, all of these subfolders will be created underneath the survey name. Then we need to move our data into the project area. So there is the transfer data option, which will do a kind of automated search and copy. But quite honestly, it's just as easy sometimes to take the data you've exported from your instrument and just drop it all into the raw folder of your project area. The next step in our workflow is to generate what's called an information file. And this information file tells the software how many lines there are and how they are positioned. So we use the create new info option on the menu, so still working top to bottom. And this will look very similar regardless of whether we're doing GPS or gridded data collection. And the only real difference is that for gridded data, we have all of our profiles listed, and then we will define the start of each line in X and Y and the end of each line in X and Y. Whereas with the GPS data, we just define the offset of the center of the GPR antenna with respect to the center of the GPS antenna, and that's done in X, Y, and Z. And then it'll also define how many GPS tags, how many positions there are per profile. Now, we would select whether, for gridded data, whether our lines are running in X or Y or both. And then for GPS or total station, we just hit the GPS button. We'd make a kind of bare bones grid to start with and then create our information file. Or in here, we just tell it it's GPS and say create information. Now, the only other alternative is that there are some kind of predetermined data types. So this is our 3D grid projects, our object mapper projects, if we're talking about Mala, or also the multi-channel system, the mirror system. And so down here, rather than using the options at the top, we can read in from the header file what the offsets are for all of the channels in the multi-channel box with respect to the GPS. And then we can simply put import create information file, and it makes the necessary information files that we would use for multi-channel processing. So once we've made the bare bones of the grid, then we actually start to edit the navigation information. And again, we have a window for GPS and a different window for gridded survey, but they look very similar. The biggest difference is you're going to notice on these buttons, which are the ones that allow us to edit the positions. So in here, it's editing the actual position start and stops of the profiles, and in here, it's allowing us to edit either offsets in distance or time and other options related to the positioning. We can, of course, have multiple information files, and that can be useful if you have subsets of a whole survey that you want to process the data separately. For example, if you've collected data in two directions, you might want to process the X files in one set, the Y files in another set, and combine them afterwards. Then we can do that in here by having an info X and an info Y, for example. You might want to split something up, so perhaps there are different surface materials and you're finding that different processing is working better on the one surface material, whereas a different set of processing algorithms works better on the other surface material. Well, then you could split the lines from the different surfaces into separate information files. Again, process them separately, combine them back together afterwards for visualizing together. Once we've created those information files, then what we can do is we can have a double check to make sure that everything looks okay. So this is especially important for the grid data. We want to make sure that all of the lines are where we expect them to be, and the green dot will denote where the start of the line is, and the red dot will denote where the end of it is. For GPS data, we get a very different window. This one actually allows us to edit the GPS or total station track. So we have a number of options in here, which includes automatically filtering the positional information based on the number of satellites, the precision that was recorded, or we can actually do it based on the line of the track. So, for example, it'll look at a number of adjacent data points, and if it sees that one of them is jumping out to the side, which obviously you wouldn't expect, it can pull that back in line with respect to the data points that are ahead and behind it. We can also export those as images, we can export those as DXFs, and we can export them as KMZ, so we can very easily have a kind of location diagram of either our grid or our positional track. Then once we've defined how many lines there are and how they're positioned, then we would go to the convert menu. And as we said, this is just taking the data and converting it from the Mala format to the GPR-Slice format. And in here we can choose to just do a straight conversion, basically just rewrite the values into a new file, or we can apply a gain, or in addition we can apply DWAL DC shift filter, which is referred to as a wobble filter. Normally in here I would avoid applying any gain at this stage, just simply run the conversion process. After we've converted, then we want to add the position stamps into those converted files. So as we said earlier, this is going to remove the need for additional positioning files. Now we've got our positional information in there, we can start to actually do some processing. And the first thing we're going to do is we're going to do any editing that might be necessary. And so this allows us to chop off data above time zero, chop off unnecessary data at the bottom of the trace, or truncate it laterally, so removing anything from the start or the end. The cutting off the data from above time zero, we can actually do an automated process on that, and we can choose to make the automation either chop the same amount off all the way along an individual profile, or we can actually get it to chop off based on every individual trace per profile. Once we've done any editing that we feel is necessary, then we can move on to actually filtering the data in the filters menu. There's all of the filters you would expect, and maybe some that might be new to you, but there's nothing missing, I would say, from here. The one that I use the most is the bandpass filter, and it's a very easy one to apply a gain. So in here we can define a gain curve either using a mathematical function up at the top, or we can simply click on the gain curve to generate a custom gain. In terms of the bandpass filter, if you decide you need to use one, left click for the low cutoff, right click for the high cutoff, and then we just hit help set, and that draws us this nice smooth bandpass curve defining where we allow data to be kept and where in the frequency spectrum we're going to remove data from. The other one, if you're making time slices, that's important is to migrate, and the reason why the migration menu is also important is that that allows us to define a velocity. So we get a synthetic hyperbola in here, and we can change the shape of that by changing the velocity and match it to our data. We can, as you see on the left hand side, define a profile of velocity. So at the moment we've got a single velocity running from top to bottom, but we could actually either we could define velocities at different depths and then ask the software to either interpolate the velocity between those picked points, or to actually step it depending upon what is causing the velocity change. So at that stage, we've done everything we need to do to visualize and interpret our 2D radargrams. So we can then go into the radar menu and pick which radargrams we want to look at and whether we want to look at them in 2D, or we can actually choose to view them in 3D space as well. So a bit like fence diagrams. Other things that we might do, but not necessarily on every data set, is apply topography. And as I said before, topography can be either just shifting the traces vertically to match the elevation at any given point, or also taking into account the tilt on the antenna to remove any strange geometric effects that we might have. We can choose to either draw a topography, so it will show us the radargram and it will show us a kind of topographic plot, and we just click with our mouse to define the topography based on measurements we might have taken in the field, or we can import them from a text file, or if it's GPS or total station data, we can just extract it from the positional files. We also have the option in here to do horizon picking, and again we can do that either manually, going through digitizing horizons that we see in the radargrams, or we can ask the software to do that automatically. And if you're interested in finding out more on that, we did a webinar on our GeoDrone GPR, and the second half of that was processing the data in GPR-Slice, where we pull out a horizon and then we process it to look at the bathymetry of a riverbed. So I've put the link to that in the chat on the right hand side of your screen, and you can go and find it on YouTube. I also said in the general workflow that we're also at the stage now where we can generate a volume for multi-channel 3D data. If all of our profiles are very, very closely spaced, then at this point we can just compile all that data into a volume and do all of our volume visualization upon it. And so all we do is we choose where we want to take the data from, so which processing step, we tell it what cell size we want, and then we generate the volume. If it's a very large volume, then we might not want to process it in one go, so we can either manually define a section of the data to compile, or we can automatically split it into blocks and the software will process each of those blocks individually, and the software will also combine all the blocks back together to give us one big data set. So we can choose whether we look at it in a whole or in sections, and we get to define how big those blocks are going to be and whether there's any overlap between them. When we've generated our volume, we sometimes might find that there's some holes in it, so perhaps our driver sort of went offline slightly, so there's a bit of a gap. And what we can do is we can decide to interpolate to fill those gaps. And the choices are to interpolate whole volume or just to interpolate into the gap, which is kind of your first port of call, because that maintains true original data across as much of your cube as possible. And we just interpolate, we just generate data values where there are empty cells. We also have the option in here for calibrating between channels. So depending upon the design of the system and how well balanced the individual channels are, this will allow us to normalize the output between the channels from the top to the bottom of each trace. And that can remove an awful lot of noise, striping in the data. Going back to our single channel data though, we still don't have a volume, we've only got radargrams. So the first thing we're going to do is we're going to generate the time slices, the amplitude maps at different depths. And so in here, this is the menu where we do this key stage of desampling to generate the coarse slices. And we have options for defining how thick a slice should be and how much overlap there is between the slices. It's always a good idea to have a bit of overlap between your amplitude maps, because that means that if you have a reflector, there's no risk of it ending up half in one slice and half in another if you overlap the slices. So we do all that, we generate the coarse slices, then we take it to the next stage, which is the grid menu, and we interpolate those coarse slices then back into something a bit smoother, which will be our final output. And in here, it's primarily this top left section that's doing the interpolation. So we're defining how much of the data we want to generate the slice from, either all of it or a subset, the cell size, the final output cell size, and then how big a search radius we're going to be using to generate that interpolated slice. So these settings are no different from interpolation in any other kind of software. Once we've made those, done that interpolation, then we can actually look at our amplitude maps, our time slices. And so here's an example at the bottom. Starting near the surface, we can see ploughing lines, a bit of near surface variation. And then as we get deeper, we can see the foundations of a building coming through. Also in this menu, we have the options for a split screen view, which is very, very useful. That allows us to plot the time slices as we have done here. Then click on any point within a time slice. It will bring up the radargram that runs through that time slice, and it will show you with a crosshair where you have clicked, so where that time slice came from. And it's excellent for being able to determine whether a feature that you're looking at in a time slice is from a true feature or whether it's some kind of artifact based on either the processing or the geometry of the data itself. There's also an option to do that the other way around. So in the radargram viewing menu, we have a split screen, and then again, click on a radargram, it will bring up the time slice that runs through that particular point in the radargram. Another really useful thing you can do is combine time slices together. So this is called overlay analysis, and it will just take the strongest reflections from a subset of the time slices and lay those over the top of each other. And that can be very useful if the target you're looking for is sloping compared to the ground surface, or vice versa. The target you're going for is horizontal and the ground is sloping, because that feature might appear in multiple time slices at different depths, but you'd like to see the kind of footprint of it in just one image. It gives you a really, really good overview. This menu is also where we generate a volume if we're using single channel data. So what we're going to do is we're going to take our list of time slices, we're going to interpolate between them to generate interim slices, interim data points, and that will generate a 3D volume for us. Once we have that volume, either from our single channel data or the volume generated from the multi-channel data, then we can go into the final button, the final view, and that's the 3D volume menu, OpenGL. And in here then we have the options to look at the data as radargrams, as time slices, as volume, which we can slice through in any direction, or we can generate ISO surfaces where we say anything with a reflection strength higher than this, please plot that cell and make everything else transparent. Once we have our data processed, either slices or volumes, then we have the option of doing some post-processing on it. So we can either do 2D processing, so that's processing on the individual slices, or 3D on the volume. We can do mathematical functions, so we can combine slices together or subtract slices from each other. The subtraction one being particularly useful if you're doing some kind of monitoring project and you want to see what has changed between the two measurements. For the 3D volume that we've generated from our multi-channel data, then we have a separate set of very specific processing tools that allow us to apply filters in 3D. And those filters include 3D migration, and we can either do true 3D migration in all directions, 360 degrees, which is very slow, or we can choose to do a 2.5D migration. So that is just migrating data inline and cross-line, so in two directions, or somewhere in between. And we do that with this angle density. So at the moment it's set to 90 degrees. So that means it will do a migration every 90 degrees. That's effectively 2.5D. But we could do it at 5 degrees, 10 degrees, 30 degrees. The bigger this number, the quicker the processing, but the less comprehensive the migration effect will be. We can do a Hilbert transform, so that's basically taking your pulse and making it all positive. So it's just saying, I have a reflection, I'm not interested in polarity, purely interested in absolute strength. And then we also have this at the bottom, this similarity analysis. But this is a way of enhancing features within the volume. And it does it by looking in 3 dimensions. It looks to see whether the data value within a particular cell has a similar characteristics to the data in the adjacent cells. And if it is, then that gets enhanced, and if it isn't, then the effect gets reduced. So it's kind of a bit like a high pass filter in a way, but it's quite a bit more sophisticated than that. And for these 3D data sets, as you can see here, this is with the similarity analysis and this is without. It can really, really bring out subtle features that might be difficult to see in the unprocessed data. So then the final stage is to export what we've created. So we have choices of exporting images, and they can be radargrams, time slices, or volumes. And we have choice of the image type that we export. We can also export them as georeferenced images or KMZ files, and that's the same for the radargrams, time slices, and volumes. We can also export animations, and again, these animations are based on the images that we create of the radargrams, the time slices, or the volumes. So it just takes all of the images, puts them into a list, and allows us then to play them in a standalone player. So we can export from here as an AVI with a range of different codecs. We can even create GIFs if you want to post something on your Instagram page or something. Then in terms of exporting data, we can export data based on our interpretation. So for example, here in a radargram, I've just been picking points, and those points can be exported as an XYZ table with the position, the depth, and I can apply a comment to that, which will also be exported. In terms of the slices, we can export those in a number of different formats to use in other visualization packages, or even just as a simple XYZ, which will go into pretty much anything. And in our 3D viewer, we can export isosurfaces, again, in a range of formats, including things such as DXFs, again, to drop into other packages. Or taking their 3D volume, converting it, as it says here, to the similar format to laser scanning, so they can combine the data sets together without a horizon, effectively. In terms of the interpretation, there are a number of options, from the very basic, just digitizing single points or horizons, to actually drawing interpretations into our volume, which can then be exported again, either as simple XYZs or into CAD as DXFs. So the final thing to look at on the interface is the blue box processing, and I'll show you this very briefly in a moment. So we would choose what type of data processing we want to do. So we've got basic, and then we can choose on top of that whether we want to do any filtering or whether we editing or both. So that would be to crop the radargrams, and this would be to apply filters. We can take a dataset that's been collected in two directions, and we can automatically process the X and Y data separately, then generate slices or volumes, and then add those together to generate a single file at the end. The reason for doing that is that if you process the X and the Y files together, you tend to get artifacts in the resulting slices and volume, whereas if you process the X and Y separately, then combine them afterwards mathematically, you get a much cleaner data set with far fewer artifacts. And then at the bottom we can choose to run Blue Box on our multi-channel mirror data as well. So when you click on one of these, it brings up another menu, and what it's saying is which of the individual steps do you actually want to run. And so we just click on what we want to do. So I want to convert the data, but I'm not interested in reversing it. I want to add the navigation markers, but I don't want to chop anything off from the data. Some of them will give you a little tick box on the left-hand side, and that actually allows you to, that will pause the process with the particular window open. So for example here, the slicing window, and that would allow me to tweak my values and do a preview of what it's going to do before I then take the next step. So if I put a tick in here, it will pause and allow me to adjust settings. If we don't, then there are generally, on most of these menus, there will be options that will be used for the blue box. So if I was in the filters menu on the right hand side of there was this RSP batch option. And if I list the processing steps that I want to do in there, it will apply those in that order. Okay, let's just do a quick real-time processing, because I realise that talking through it can be quite confusing, and it feels like it's a very long process. But hopefully, with the last few minutes, I can show you that it really isn't. So we start the software and the splash screen comes up, click on that, and we go into the projects, and I'm going to just say File, Create New. I'm going to just skip to my default directory, which is C, GPR data, slice projects, and then I'm going to call this demo 1. And it's a GX dataset. So new survey, creates all the subfolders, and I can then close this down. And now I want to copy the data into the raw folder. So I will just go onto my desktop where I've got some demo data. I'm going to grab all of my files out of here, find my project folder. So slice projects, there's that new one, demo 1, that's what I've just created. I'm just going to drop all of the data into the raw folder, back to GPR-Slice. So keep going down, transfer the data, create a new information file. So this is a grid file. The lines are running north-south. I have 41 lines, And this is the kind of static part of the name. So if I look in the folder, see it's dat underscore and then 4 digits. So dat underscore 0000. They're RD7 because it's come from the GX. The GPS is irrelevant at the moment. The name is going to go up one at a time, and the lowest file number is 1481. Profile name start 1481. They are every half a meter, so it's going to start at 0 in X and it's going to end at 20. And the length of the lines is 40 meters, although we could actually leave this blank and extract that directly from the header file. Same with the information about how long the time window is, and also how many samples there are per scan. So I can just hit create info now. And so because there are 41 files and I've told it starts and ends at 20, then it's evenly spaced them all every half meter. And you can see that I've got 0 in the Y columns at the moment. So close that down. File, edit information now, next one down the list. Marla get TS first of all. That's time and samples, so it's updating the values that it's found for the number of samples per scan and length of the window time. And so that's put those values into the box down here. Now I need to make sure that the Y distance is correct, so I can just say Marla get XY. It will read the distance from the header file. It's asking me if I want to round the survey wheel to the nearest range unit. I say yes I do, because I know this was running from long tape measures from one side of a grid to another, so just say yes. And as it stands, we've got probably a bit of an issue with the odometer wheel. Maybe the user didn't actually calibrate the wheel at this location. So what I can do is I can actually just force the issue here. I'm actually going to edit any that aren't on 39, because the majority of them are. I'm just going to say save edits, and then I'm going to select the top profile. I'm going to put the value 1 in here, and I'm going to add that to the Y1 column. So add 1 to Y1. Okay, so they're all 40 now. Save edits and close this down. File, grid plot. So at the moment, the software thinks that all the lines are running in the same direction, so I am going to have to reverse some of these. But first of all, I need to convert it to the GPR-Slice format. So carry on down, convert data. It's Marla 32-bit to GPR-Slice 32-bit. There is no WOW to DWOW, and there's no DC drift in this HDR data. It's very, very good. So I can just say batch gain. And we can see at the top here, it's working on those. This is doing the multi-thread processing for me. And as I said, just converting now. So it's taking it from that raw folder, putting a copy of the new format files into the radar folder. Okay, so close that down. If I look in the folders, see now raw data and data in the radar folder. Next, reverse. It's all the even ones, so I can automatically select those, say save edits, start reversing. And you can manually switch on and off in this, or you can choose one of the other auto picks. So that's done. Next, along the menus, navigation, need to put some markers in, so I'm just going to put artificial markers in. Done that. Next, we're going to go to the radargram editing. And I'm going to take the data from the radar folder, and I'm going to automatically detect time 0 and run it so that it's line by line rather than every trace. I just want time 0 to be picked at the same point all the way through each traverse. So auto 0 nanoseconds, line by line. I'm just going to leave this on the default settings for the moment in terms of the detection. So it's running through each line, looking for where time 0 is, and it's going to report back to me as to what those values are. fairly consistent, not too bad, so I'll accept those. And then now it's going to make the adjustments. It's going to take the data out of the radar folder and it's going to dump it back into the edit folder. So that's great, and it's written me a new information file with an updated number of samples per scan because we've cropped the profiles. Okay, then I'm ready to do my filtering. And as I say, first thing I'm probably going to do is bandpass and apply a gain. So we hit Spectra plus gain to have a look at the data, and what we can see is we haven't got any gain applied at the moment. This is our data. This is the trace before any filtering or gain is applied, and this is what it would look like afterwards. So one thing we can do is we can apply an AGC across the data, which may or may not work to your advantage. Alternatively, what we can do is we can bump the gain up manually, and you can either use the plus and minus buttons on the right hand side, or you can actually just click and shift the nodes with the left mouse button. And this is really just depends how confident you are, how well you know the site, how well you know your instrumentation, as to what kind of gain curve you decide to apply. So I'm just going to stick with that for the moment. I can edit my high and low cutoffs for the bandpass filter, and this will act in real time as the gain did. So for example, if I was to drop this right down low, I'm basically just seeing very low frequency. If I pop it right up high with the left and right mouse button, then pressing help set, you just see very high frequency banding. And what I want to do is kind of place it somewhere around the kind of active frequencies of our 450 megahertz antenna. So I'm going to stick with something like that for now. So I'm going to close that down, and I'm going to hit hit the bandpass button. Now, when I did the zero removal, I had the multi-thread processing switched on, and that means you don't get the option of processing graphics. If you have multi-thread off, then every time you process a line, you can have the option of seeing a before and after plot, which works quite well. But obviously that takes longer because it has to do each file sequentially, whereas if I hit multi-thread and then redo it, it'll be way quicker. So when you first have a look at the data, I tend not to have the multi-thread on, and I tend to have the processing graphics switched on so that I can see what the steps are doing. And then once I'm comfortable that I've got good settings, then whilst I'm tweaking various other things, I'll just run it in the fastest way possible. So that's done. Next one would be probably just a background removal. So I need to now take my data from the bandpass folder where it's been written to, and then just hit background. And this is just taking effectively the average trace away from the profiles. The window length is kind of infinite, so it's just the entire profile that it's doing the background removal on. Okay, and then from there I'm going to do some migration. So hit the filter folder, that's where the data was put after I did the background removal, and then do search. And let's make this fit my screen a little bit better. And then look for one which has some relatively easy to spot tails. And we can always test it, so we can hit test migration. And we can see that we've tidied up the edges of some of these features. That velocity might be a little bit on the fast side. Unfortunately, this site doesn't have any very useful kind of utilities to give you a really nice, clean test. Let's try that. There we go. That's pretty good. Use that for the moment. I might just want to up the gain a little bit. And again, you can choose if you want to just have a look at a few lines when it first starts, then switch the multi-thread off and it will do one line at a time, and we'll be able to see the before and after pictures. So I might want to just up the gain a little bit on that. And then I'm going to switch the multi-thread on again just to speed things up and run the processing. You can see here that it's starting the processing from sample number 3. So that's applying the migration to the whole data set. The reason why it's 3 and not sample number 1 is that the positional information that we include in the data are stored in the top 2 samples. So sample number 1 and number 2 carry the position stamps. So any processing we do will always begin from sample number 3 downwards. And I always feel really bad when I do these demos using my computer, because it's a bit of an old dog. It's had a fairly hard life out in the field. Migration is probably one of the more demanding of the tasks that you're going to make the software do. And then once we've done this, that's all of the processing done. I'll be able to look at the radargrams, and then we'll make the time slices. We'll have a quick look at those, and then we'll put it into a volume. Okay, great. So if I go to radar, 2D radargrams, and I'm going to view all 41 radargrams. I'm going to view them in 41 rows, and let's make that a little bit smaller. That's coming out of the bandpass folder. If I put it into the migrate folder, then I can see the slightly more processed data. If I want, I can actually overlay these on top of each other, and then I could export every time a new file is written. And I'll actually use the auto name. So this is just cycling through, drawing each of the radargrams. I'm going to stop it partway through now. If I go to the folder, I've now got radar and then a number for the number of the file. And if I click on that, I can see those. So obviously we can edit the way those appear. We can edit the color scales. We can edit the axes. We can edit which section we look at. We don't need to look at all of it. We can crop that down. Now I'm going to move on to generating the time slices. And so what we need to do is we need to say how thick we want our slices to be. That's usually the thing I start with. And for this data set, I'm going to try and get something that is about 20 centimeters thick. So at the moment we can see that the thickness is 18 samples, and in the list up here that shows me the slices, I can say that those are 15 centimeters. So I need to make this a bit bigger. If that's 18 samples is 15, then yeah. So now I've managed to make my slices about 20 centimeters thick, and what I want is to have a 50% overlap between my slices. So I want 0 to 20 centimeters, 10 to 30, 20 to 40, 30 to 50, and so on all the way down. The easiest way to do this, rather than trying to fiddle around with the start and end sample and how many slices you have to try and get that correct, is to use this little help set device. So I've defined how thick it was, and I want a 50% overlap. So I just say help slices. Tell me how many slices I need to cut from the top to the bottom of my profiles at this thickness with 50% overlap. So help slices. Right, I need 20 slices takes me from top to bottom. If I say show example, it doesn't look right. That's because I am pulling the data from the wrong folder. I'm pulling it from the just raw converted files. So I want my migrated folder. Show example. That looks a bit better. So you can see slice 1 in red, slice 2 in blue, slice 3 in red, slice 4 in blue, and so they all neatly line up with a 50% overlap. Then define how many bins per mark I want. So markers are every meter, and I'm going to say 4 bins. So that is effectively a 25 centimeter bin, and that is approximately half my line spacing, which is kind of the sweet spot for this. And then also give the slices a name. So they're just called slice, and if you want to remind yourself what you've done to it, I could say bandpass background migration. So I now hit slice X, Y, Z, and that is taking each of the radargrams, chopping up the data into these coarse bins, and then generating the horizontal slices from those. There's my slices being created. And close that down, go to the next menu along, that's the grid menu. So this is going to interpolate those coarse ones into the final product. Simple thing is just to say help set, and I'm going to use fine cell size and standard search radius, and then just hit start gridding. And at the moment I'm doing an inverse distance because that's quicker. The kriging will tend to give you a better, sharper image. And if you want to use the kriging, then if you hit the variogram button, it'll look into your data set and it'll extract the necessary statistics to fill in the range, nugget and sill values. Okay, job done. Now go to my pixel 2D time slices. And choose my data set I want to look at. And make 100, draw. Could have done that better. Let's put that into 3 rows. So those are my slices. If I left click on one of them, then I get the plotting options. And what I'm going to do is I'm going to ask it to auto gain each of these. So I'm going to set the plot parameters based on the mean and standard deviations. So run that for every slice. And then I can also, if I want to, perhaps change the color and say redraw. And those are my time slices. And as I did with the radargrams, if I don't want to look at all of them in one go, or I want to export every image, I can say that make them a custom size. Don't put any shift so that every time it plots a new diagram, it isn't shifted in X or Y from the previous one. And I use the auto identifier and just say draw. It's firing out my data like that. I'll just cut it short. And then if I open the folder again in my JPEG, I have the slices and their name, the name of the slice itself from the processing, and then it will give you the thickness in terms of the time and also depth. And obviously the depth is based on the velocity that we're using. Click on one of them and I can have a look at it. At the moment, I don't have a 3D volume, so if I use the 3D viewer, all it will do is it will show me the radargrams in 3D space. So like I say, a bit like a fence plot. So I can scroll through those. And I can store one, and then I can put another one in. Yes. And there's various things that I can do with that, but we'll come back into that once we've got the volume. The other thing that we could do was the split screen. So draw my radargrams again. Time slices, sorry. And then if I click on one of the time slices, it'll open up the radargram and it will show me the thickness of the slice, and the crosshair is the point that I chose in the time slice. So let's just put these side by side. So you can very clearly see what it is that is creating the response in the time slice itself. Okay, close those down. I'm now going to make my volume. So pixel menu, 2D time slices, and just come down here. I put how many interpolations between the slices I want, and then the output name, and I'm just going to stick with the default name here. Job done. OpenGL, and here's my volume, which I can scroll through. I can store a slice like that. I can put in a radargram like that, and I could, if I want, put an isosurface in. And if I just make the vertical scale slightly less mad. It's very easy for us to make our visualizations. So as I say, we can export images and animations out of here very simply. Another nice tool is the in the 3D volume is to have the XYZ 2D view, and with this one what I can do here is I can click my crosshair in the volume and it will update with a cross section through the block at that point, and also show me the nearest radargram. Then if I scroll down through the volume, we can see that the crosshairs move down through the cross sections and also through the radargram to show me exactly where I am viewing. We can sort of do this the other way around, so we can actually do what's called a radar sync. So I pick a radargram, hit the R sync button, and now as I move my mouse through the radargram, you can see that the crosshairs move to update with my mouse, and the depth of the volume also changes with the mouse. So all that's happening in real time. Now at the moment all of that data were collected on a grid with no positioning. What I could do right at the beginning, if I had some positioning information, would be to, in my edit information file, is to define the location of the first file. So if I just I have those values here, so let's just put them in. And hit georeference info. to just do the navigation. Yeah. Yeah, recompile my slices. Call these ones GPS and take the data from the migrated folder. Close that down and then grid them. So hit help set so I get the new extents of the data. Make the cell size a little bit bigger just to make this quicker. So start gridding. Okay. Pixel 2D time slices. Generate a new volume. Make sure that I've got that new volume selected. GPS, yep. OpenGL. Right, here's my data. What I can do this time is I can come in here, say bitmap image, get a Google image. So that will hopefully pick out where this data were collected from, where these data were collected. Store the map. Close this down. Close this down. And then I got my volume in situ. If I want to, I can change the position of that. So bitmap image. If I change the depth to 0, 0, 0, and 0. Now my cube is underneath. I can change the transparency of this so I can see what's underneath more clearly. And then I can put in the volumes, or I can scroll through. Also have the option now to actually cut out the overlying image completely, which then basically gives me a box into which the data are plotted. And again, I could do my ISO surface into there. And see exactly where that data sit. Okay, so that's a very quick run through of a regular single channel grid data set. And now what I'm going to do is I'm going to use the blue box processing just to quickly process some concrete data. As before, create a new project. This is from our CX instrument, so Concrete Explorer demo, and it's Mala CX12. I'll find my CX data, copy that, then place that into the new project area. So Slice Projects, CX Demo, Raw. And with the CX, one of the things we can do is we can set out a small grid on the floor, collect in X and Y direction, and then all that data is multiplexed into a couple of files, one for each direction. We can process it on the instrument. I'll just be able to see in the background there the rebar mesh visible on the screen. But then obviously we can post-process it in something like GPR-Slice. So Because this is a very small data set, that square is less than a meter wide, I'm going to need to change some of my options. So instead of working in meters, I'm going to set everything into centimeters. And then I'm going to say create new info. And down at the bottom here, I'm going to select the Mahler 3D star.rd6. So these are these multiplexed files. So all of the X files are in one, and all of the Y profiles are in the other file. And so this has now created that main, info main, and also info XY, which is the data files you would have if it wasn't multiplex. So there's a line for each of the X profiles and a line for each of the Y profiles, but these aren't actually filled with data at the moment. It's still all in these. So things that I'd want to do are change the number of units per marker. So now instead of units per marker being 1 meter, the unit per marker is 10 centimeters. So do that. Save that for both of these. And first thing I need to do is just extract the individual traverses from the two multiplex files. Switch to the info XY. And then normally you would need to do a little bit of investigation in terms of what values you're going to use for your blue box processing. Fortunately, I know this data set quite well. So what I can do is I can just plumb in the numbers that I need in the filters section. So I know it's quite a fast velocity, it's very dry concrete. I know roughly what my migrator width needs to be. I know approximately what gain I need to apply to the migration. It's a 2.3 gig antenna, so I can put in some suitable cutoff values for that. On the bandpass filtering, and the processing steps I'm going to take are background removal, and I'm going to make that pretty harsh on this, followed by the bandpass, followed by migration, followed by a Hilbert transform. On the radargram editing, it's going to be line by line, and I know what values to put in there. So this is just, you'd normally do a little bit of trial and error, but of course if you were doing a lot of these panels or a lot of areas on the same kind of concrete, you're going to have the same processing values for the majority of them. So then I go down blue box, and it's the XY decoupled gridding plus editing plus RSP, radargram signal processing. And it's decoupled gridding, so what it means is it's going to process, combine and grid all of the X data, then all of the Y data, and then add them together afterwards. So I want it to convert. I don't need it to reverse. They all start at the same side of the grid. I do need navigation. I do want radargram editing. I do want to do the signal processing. I want it to slice and I want it to stop so that I have some input on that. Then it's going to grid, and the values for the search radius are given to me automatically based on the values in the information file. Then the grid math, this is how it recombines the X and Y datasets, and actually it's best to use the second option. If you use the X plus Y, where the profiles cross, you can sometimes get hot spots because the reflection strength is superimposed, whereas here what it does is it just takes whatever the strongest value for every pixel is in either the X or the Y, takes that and puts that into the final slices and therefore the final volume. then a slight smoothing low pass filter on the data, and then create the volume and then open GL. So let's give this a whirl. Oh, I might just switch off the multi-thread. It is off, that's good. So you can just see everything that it does. It will make it a bit slower, but you can see how it's running through everything. So let's run it. So converting the data. Navigation flicked up there. This is the radargram editing. This is the background removal. Bandpass filter. Migration. Hilbert transform. And now it wants me to define how the slices will be generated. So let's just, again, it's a data set that I know relatively well, so I will use some kind of previously tried settings. So this is now, it's generated the coarse slices, this is now doing the gridding. X data set first. Now the Y data set. Now it's going to do the low pass filtering on the grids. Now it's going to add the grids together. Sorry, this is the low pass filter on the grids. Now it's plotting them and creating the 3D volume. And here we have it. It got a bit of a strange artifact around the edges, but I'll just ignore that for the moment. Scan through, see my top layer of rebar mesh and the bottom layer. They actually overlap, and it's clearer to look at this in the ISO surface. So if we ignore our artifact around the edge, then that's our model. So store that, put in the Zs. And that's basically how it works. If I was to redo this, switch off the processing graphics, switch on the multi-thread and then run it again, it'll give you an indication of how quickly we can do this. And so obviously if you needed to just tweak some of the settings, you could pop into the whichever menu needed it, change the value, run it again, and you're only talking about a few minutes work. Ooh. Just change this and then let that run. And now we're gridding the two directions. We've overrun slightly today, I'm afraid. Sorry about that. But I'm still available for questions at the end of this. And if there's any more, don't be afraid to ask. And as I said, the plan in the future is to actually do slightly more focused sessions where it's kind of easier to fit stuff into an hour. So that might be a particular product, a particular method, a particular type of processing, or a particular application. So if there's any particular requests that people have, do please feel free to send them to us and we'll put them on the list for things to cover. We're just doing the final stages now. Hopefully you will have our volume. So you can see it's quick, especially if you have the processing graphics switched off. And there we go. Okay, and so with that, I've finished the formal part of the presentation, and I'll open it up again to some questions if there are any left.